The word modeling essentially means working application problems, except with modeling, we also need to create the problem that we're going to solve. We need to write out or develop the mathematical model that describes the phenomena that is occurring that we're looking for a solution to. So we're going to do section 2.3 here, pretty much as it is in the book. I'll take a look at a mixing problem, although we actually already did one of those. I did it in section 2.2, separable differential equations. It's sort of the back half of that video. So if you want another example of a problem like that, feel free to go back and take a look at that video. We will do an example like number 2, like example 2 in your textbook, compound interest. I will address example 3, chemicals in a pond. I guess I should write these down. Example 3 is chemicals in a pond. I'm not actually going to work through a problem like that though, but I will address why when I talk about that question. And example 4 is escape velocity. So I'll take a look at that as well. Escape velocity. So we have already done a problem like this. I'll do another one. We'll do a problem like this, compound interest. I will address one like this, but I won't actually do it, and I'll explain why, and we'll do one like this. All right, so we're going to do 3 problems together like the ones in your textbook, but not those exact problems. I'll give you some different problems to have in your repertoire. So that way you'll have an example in the textbook and another example, a different example from this video. So we'll start with the mixing problem. I think I'll do each of these in a separate video. So this first video is just going to be the one about mixing. At the end of this video, I'll address example 3, chemicals in a pond, because that's where it's most appropriate to do that. So look for that at the very end of this one. Here's the problem we're going to be working for this example. A tank contains 80 gallons of fresh water. A salt solution with 2 pounds per gallon of salt flows into the tank at 2 gallons per minute, and the well-mixed solution drains out at the same rate. So we have 80 gallons of fresh water. There's no salt in it at all. Some salt water. The salt water that goes in has a constant amount of salt in it. Every gallon of water that comes in has 2 pounds of salt in it. And it flows into the tank at 2 gallons per minute. Okay, so each minute we have 2 gallons coming in, and each gallon has 2 pounds, so we have 4 pounds of salt coming in per minute, but it's coming into fresh water, or starts out as fresh water. The well-mixed solution, so we don't have to account for any variables or variation in the amount of salt in one part of the tank versus another. The assumption here is that the amount of salt in any eyedropper full that you take at any moment in time will be the same as any other eyedropper full at that same moment in time. And then the solution drains out at the same rate as it comes in. Okay, so it's coming into the tank at 2 gallons per minute. It's also going out of the tank at 2 gallons per minute. And what we're going to be looking for here is the amount of time it takes to get the tank to a place where it contains exactly 1 pound of salt. In order to do this, we need to have an equation that models the situation, and then when we solve the equation, we'll have the answer to our question. Your textbook says it's going to use Q of T to represent the amount of salt. I think Q probably stands for quantity. The amount of salt in the solution at time T. Well, that tells us, or we can say from this, that the rate of change of the amount of salt in the solution over time is the rate at which the salt is coming into the tank minus the rate at which the salt is going out of the tank. Now notice I'm talking about salt here, not salt solution, right? The amount of salt is, for example, here, in 1 gallon of water, the amount of salt is 2 pounds. So here, we have the amount of salt. Q is the amount of salt in the water at time t, and this is the rate of change of salt in the water. The rate at which this amount of salt is changing is the rate at which it comes in minus the rate at which it goes out. Well, the rate at which it comes in is 2 pounds per gallon. It's tempting to say that's our rate in, but that's the amount of salt that's coming in for each gallon, right? That's not a rate. The rate is the amount of salt per gallon times the 2 gallons per minute. And then if I cancel these labels, I'm left with 2 pounds per 2 minutes. Sorry, 2 pounds times 2 per minute, or 4 pounds per minute. That's a rate. Okay, that's going to be equal to that. And then I have to subtract the rate out. It's tempting to say, well, the rate in minus the rate out is 0 because the fluid is flowing into the tank at, well, I can say it's flowing out of the tank at the same rate as it's flowing into the tank, but that's the rate of the fluid, right? That's the rate of the solution, not the amount or the rate of the salt. So to find the rate of the salt, I'll have to figure out how many pounds, or how to represent how many pounds per gallon, and multiply that by the rate, which is also 2 gallons per minute. And then I'll be able to cancel those labels, and I'll have 2 times some number of pounds per minute. In fact, I can write that as pounds per minute, but I still need to figure out what goes here. If we look back at the rate in, we have 2 pounds per gallon times 2 gallons per minute. And the 2 pounds is the number of pounds of salt. The 2 is the number of pounds of salt in each gallon of water. We don't know that here. But at any given time t, we've set up here, it's going to be Q. So this is going to be Q. This Q. And actually, this needs to be Q up here as well, now that we know what goes there. And then when I cancel my units, I get Q pounds times 2, so 2Q, forgot my 2, 2Q pounds per minute. And I'll simplify this. This is going to be 4 minus 2Q. And of course, our labels, our units will be pounds per minute. But this is dq dt, just as it was before. I've just been sort of modifying my equation. So now what I have is a differential equation that I can solve. dq dt equals 4 minus 2q. And then I can either solve it using an integrating factor or treat it as a separable differential equation, depending on which form it actually has. Well, this one, it turns out, we can treat either way. We can either add, let's see, if I divide both sides by this quantity and multiply both sides by dt, I get 1 over 4 minus 2q dq equals dt. And now if I integrate both sides of this equation, I'll come up with an equation for q of t plus a constant. On the other hand, I can do it this way, or I can do it this way. If I add 2q to both sides, I get this equation, which is in the form that it needs to be to use an integrating factor. And we're going to do it that way just because that's a newer concept and it would be useful to get some extra practice. But I encourage you to go back and, once you've finished watching this video, or maybe pause it now and try to work it out this way and see what you get. You should get the same thing as, it may be in a different form, but you should get the same thing as I do here. All right, so what is my integrating factor? My integrating factor is going to be, I'm going to highlight a couple things here. We're going to do this process, not the other one, and so therefore I need an integrating factor. And the integrating factor is e to the power of the integral of p dt. But what is p? P is the thing in this equation, in this form, in this position. So it's just 2. So it's actually going to be a very simple integral to do. I'll just do it here. The integral of 2 dt is 2t plus c. That, of course, simplifies to k e to the 2t, because this is e to the 2t times e to the c, which is a constant. And I just have a tendency to call my e to the c constants k to help lessen the confusion between what constant is playing what role where. So because we're working with an integrating factor here, we don't care about the c's and we don't care about the k's. So I'm actually just going to use the integrating factor e to the 2t. Now that I know what it is, I'm going to take my equation dq dt plus 2q equals 4, kind of given myself enough space, but in the wrong place, really. And I'm going to push through a factor of e to the 2t. What I'm really doing here is multiplying. I've got an equals where I should have a plus. Sorry about that. Let's get this tidied up first, shall we? What I'm really doing here is multiplying both sides by the integrating factor e to the 2t. But when I do that, I end up with e to the 2t dq dt plus e to the 2t times 2q equals 4e to the 2t. Now on the left-hand side, I have a function times the derivative of the function q plus the function q times the derivative of this other function, 2 times e to the 2t. Let me rewrite this in this order. Maybe that'll make it easier to see. 2 e to the 2t. If the function is e to the 2t, the derivative of that function is 2 times e to the 2t using the chain rule. If the function is q, then the derivative of that function is dq dt. So here I have a function times the derivative of a second function plus the derivative of the first function times the second function. And the right-hand side is just the result of having pushed that e to the 2t through. This left-hand side here, though, now is the derivative with respect to t of the product of the two functions, e to the 2t and q. And what's left to do now is integrate both sides with respect to t. On the left-hand side, everything goes away except for the integrand, because I'm taking the integral of a derivative. So I have q times e to the 2t equals whatever this integral is. We'll work that out in a minute. And then I'll just divide through by e to the 2t, leaving me with q equals. And that's what I was after. So let's see if I can figure out where I'm going to do this. I think I'm going to try to squeeze it in here. So from there, I'm going to go up here and I'm going to say that my left-hand side now is just q times e to the 2t. And my right-hand side is the integral of 4 e to the 2t. Well, the integral of e to the 2t is 1/2 e to the 2t. When you multiply that by 4, you get 2 e to the 2t plus c. I could have put a c on this side, but it would just be absorbed, or I could absorb it over here. So that I've put it on this side. And what's left to do now is to divide everything, divide both sides of this equation, the equation we have at this point, divide everything by e to the 2t. So now I have q equals 2 e to the 2t plus c all over e to the 2t, which if I split that up into two fractions gives me 2 e to the 2t over e to the 2t plus c over e to the 2t. And this is our general solution to this differential equation. But we've used this differential equation to solve a real problem. So now we need to go back in and figure out how to use this information to answer the original question. I think I'm going to have to erase some of the screen. I really like not to do that whenever possible, but I think, I'm out of room. So I think what I'm going to do is erase much of what's on this side. So if you need to, pause the video and write some things down and then come back and join us. Okay, let's erase this part, first of all. We've used this radian, we've used that to create our equation, so I can erase that as well. And then I'm going to rewrite my answer, my equation here, Q of t equals 2 plus c over e to the 2t. Now, in this case, I do care about the c, because the reason I didn't care about it here was because I was using an integrating factor. I can use any integrating factor I want, as long as it will produce this. Let me highlight in a different color. I want to produce this derivative of a product, right? That's what I'm after. And so I can use any integrating factor I want that will do that. So I use the simplest one. Having come up with something here, I'm going to use the simplest one that I can. But when I get to the point of solving the differential equation and coming up with an answer, a general solution, I very much care about the c. And in this case, we need to use the information, the rest of the information in this question to figure out what c is. Now the question is, determine the time when the tank will contain 1 pound of salt. So I need to put in a 1 for Q of t. Q of t is the amount of salt at time t, and then solve the problem for t. But I can only do that if I know what c is, and I can use the fact that the tank contained 80 gallons of water at the very beginning, and it was fresh water, so there was no salt in it. So I have this other piece of information. Q of 0 equals 0. There is no salt, 0 salt, at time 0. If you look at this equation right here, we have one unknown, the amount of salt, Q of t. We have another unknown, t, and we have a third unknown, c. Well, here's a pair of unknowns. These are paired. There's going to be a different amount of salt at a different time, but these two values go together. So what I can do is say when, let's do it by highlighting. When Q of 0 equals 0, let me rephrase this. When t equals 0, these are all representative of t, and I'll use, blue. Then Q of t, the amount of salt, is represented by Q of t, or Q of 0, and we can do some substituting. So when t is 0, I'm going to write this down here. When t is 0, plus, I have e to the 2 times 0, because t is 0. And when t is 0, Q of 0, Q is also 0. So my left-hand side is going to be 0. And then I'm just going to solve this. E to the 0 power is 1. So I get 0 equals 2 plus c over 1. So negative 2 equals c. Now I know what c is. I can plug it in up here. So I have a formula for the amount of salt in the tank at any given time is 2 plus c over e to the 2t, and I now know c to be negative 2. So I'm going to make that a minus 2. All right, I'm going to erase a little bit of stuff here, give myself some more room. Cordon that off as well. So now I need to figure out what t is when the amount of salt is 1. So let's substitute that in. We have, I'm going to kind of go over here a little bit. 1, the amount of salt we want, 1 pound, is equal to 2 minus 2 over e to the 2t. solve that for t? Well, let's subtract 2 from both sides. I get negative 1 equals negative 2 over e to the 2t. So positive 1 is going to be equal to positive 2 over e to the 2t. That means e to the 2t, multiplying both sides by e to the 2t, gives me e to the 2t equals 2. Exponentiate, nope, take the log to, come on, pencil. It's not working. There it is. 2t equals the natural log of 2. So t equals ln of 2 over 2, which is approximately 2.89 minutes. 2.89 minutes. So it takes the amount of salt in the tank to, sorry, I was looking for my highlighter. There's my final answer. It takes 2.89 minutes for the amount of salt in the tank to go from nothing to exactly 1 pound if the rate of the flow in is 2 gallons per minute and the amount of salt per gallon is 2 pounds per gallon. So that's a mixture problem. It's similar to the one we did in the earlier section, but it's a little different in what we were looking for here. I found an error. This is the wrong value here. When I wrote this down, I wrote it correctly, the natural log of 2 over 2, but when I typed it into my calculator, I typed it as 2 over the natural log of 2. So it gave me the wrong value there. So I'm going to correct that. It should be, get the right pen tool here. It should be 0.347, we'll call it. The only other thing I wanted to do with this example is to say that I did go back and do this problem the other way. I wrote it as a separable differential equation and I solved it that way. And the equation I came up with, my differential equation, looked slightly different just because of the algebra that I did to get to it. But it's the same equation. It's the same function of t. It's 2 minus e to the negative 2t. So 2 minus 2 e to the negative 2t. And so if you take e to the negative 2t, you can write that as 2 over e to the 2t. So you get the same differential equation, and of course, when you go forward from there, you get the same value. Okay, I promised you a look at example 3, even though we're not going to work through this one at the end of this video, and here it is. Here's the problem. So let me just read through it quickly, and then I'll talk about why I don't feel like we need to do this problem. Consider a pond that initially contains 10 million gallons of fresh water. Water containing an undesirable chemical flows into the pond at the rate of 5 million gallons per year, and the mixture in the pond flows out at the same rate. The concentration gamma of T of chemical in the incoming water varies periodically with time according to the expression gamma of T equals 2 plus the sine of 2T grams per gallon. And then we're asked to determine the amount of chemical in the pond at any time. Well, this last sentence here basically just says, write a mathematical model that describes the situation here. Write an equation that models the problem at hand. So that's all this one here says. Because we're looking for the amount of chemical in the pond at any time, we're looking for a general solution, not a particular solution. So we're not looking for, there's 17 grams in the pond at a particular at a given time. We're looking for the general solution where if I knew what time I was interested in, I could plug that value into my answer that I'm going to get here, and I could find out then what the amount of chemical was at that particular time. But the answer to this question will just be a general solution. Now, here's why I don't think we need to do this problem. If instead of a pond, you have a tank, and if instead of 10 million gallons, you have, what did we have? 80 gallons of fresh water. And if you have, instead of an undesirable chemical, you have salt, and you have a flow rate, instead of 5 million gallons per year, you have a flow rate of 2 gallons per minute. With those changes, this problem is exactly like the one we did a minute ago. It's the same problem. It's just a different environment, but the parameters are identical with one exception, and that is this one right here. The incoming water varies, right? The concentration of the chemical in the incoming water varies according to this equation. Well, the concentration of salt, or the concentration of this undesirable chemical, is just how much of that stuff there is in the water. So this is really just like saying how much salt is in the water. Not how much water do we have with salt in it, but how much salt is in the water that we have. You'll have seen this down here by now. I wrote the equation that we started to come up with, or the beginnings of working with that previous problem. I wrote that down below here because I want to take a minute and just substitute a few things out. In the previous problem, as with this one, the rate of change of the stuff in the water is represented by this expression here. The rate of change is the change in the stuff, the change in the amount of salt or the amount of chemical over the change in time. And with our previous problem, we had 2 gallons of water per minute coming into the system, and then 2 gallons per minute going out. In this problem, we have 5 million gallons per year. So let me change that. Instead of 2 gallons per minute, we have 5 million gallons per year. Same thing here, 5 million gallons per year. Now, the concentration, this expression right here, replaces the concentration of salt in the water. Well, the concentration of salt in the water was 2 pounds per gallon. So this expression gets replaced. I'm going to put this in a different color, I think. This entire factor gets replaced by 2 plus the sine of 2t grams per gallon. And then, of course, I'll be able to, in this term anyway, I'll be able to cancel that unit. Now, Q represents the amount of salt, or in this case, the amount of chemical in the water at time t. So instead of Q here, we need, because we worked with a concentration here, we need to work with a concentration as well. And that is, let me get a different color pen. Q is the amount of stuff in the water, but we have 10 million gallons. 10 million gallons. So we have Q grams for every 10 million gallons. So we can write this as Q of T, or just Q, let's just write it as Q for consistency, divided by 10 million. And your textbook does this way, and I'll do it at this point too, just to save space. 10 to the 7th power grams per gallon. And if you notice over here in my concentration factor, I also have had grams per gallon. So now when I replace Q with Q over 10 to the 7th grams per gallon, I can also cancel that. Oops, wrong color. Gallons there and gallons there. So now my expression, or my equation, is dq dt equals, well, there's a little bit of arithmetic and algebra going. This whole thing is replaced by this. So I have 5 million times this. Let's write that as 5 times 10 to the 6th. Oh, it looks like it doesn't need to be a fraction. I can move that down just a little bit. 5 times 10 to the 6th times 2 plus the sine of 2t minus q over 10 to the 7th. Now watch this. This is 5 times 10 to the 6th. Let me write it that way. 5 times 10 to the 6th. And if I borrow, let's see, I'll use blue. If I borrow one of these tens, then I get 10 to the 6th here. So let's write that as 10 times 10 to the 6th. And then I can cancel my 10 to the 6th. We'll do that in white. 10 to the 6th and 10 to the 6th. But I have 5 over 10, which is 1/2. And my numerator here, all that's left, I've reduced this, right? All that's left is q. So there is my differential equation. It is slightly different in this piece here than the previous problem. But when you distribute this, it's a large number, but it is just a number, it's a constant. When you distribute this across this expression here, you get a constant here, you get a coefficient times sine of 2t here, and you get an expression of q here. So with that information, you should now be able to finish this problem out using either the separable approach, is this a separable differential equation, or the integrating factor approach. Now I'm going to let you read through the rest of the problem. This is the exact problem that comes from your textbook, and so if you're using the same textbook as we are, this is example 3, which begins on page 44. We're in section 2.3, and the book does an interesting little thing with this number here. It represents q with little q and calls the units something else. So that gives us a smaller number to work with in our problem, but the principle is the same. The textbook uses the integrating factor approach, and I would ask you, why did they not do it with separation of variables? I'm going to leave you to sit with that. That's going to be enough for this video because it's really quite a long one. I spent longer on this page than I really meant to, but that's enough for this one. We'll take a look at a different example in the next video.